Hi, my name is Matt Rodell. I'm a hydrologist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Today I'll be talking with you about monitoring and forecasting wetness and drought using data from NASA's GRACE and GRACE follow-on satellite missions. Next slide, please. If you want to monitor water cycle variables related to wetness and drought, there are many ways to do so using in situ measurement techniques. However, what they all have in common is they're labor-intensive, expensive to install, and you just can't do it everywhere. Next slide, please. These maps show the locations of measurement stations around the world for various types of observations. The upper left shows surface meteorological observations locations. These include things like precipitation, temperature, and wind speed. And you'll notice that the observations are fairly dense in the more populated parts of the world, such as the United States and Western Europe. However, in other parts of the world, such as North Africa, Siberia, Central Australia, there are many places where it might be 100 or more kilometers between observation sites. The lower left shows the locations of river flow observations that are archived by the Global Runoff Data Center in Germany. The warmer the color, that means the longer since the observation record has been updated. So for example, you can't get an observation from the Nile River in Egypt later than about 1983. The lower right shows the locations of the USGS Groundwater Climate Response Network. These are groundwater monitoring wells that have a long enough record and frequent enough observations that are useful for looking at interannual variability. It's a fairly dense network in the northeastern US, but in the rest of the US, there's some large gaps. It's even worse when you look at the global map of groundwater observations shown in the upper right. You see that the US is fairly well covered compared to the rest of the world. Many of the nations of the world don't provide any observations for this groundwater network. Next slide, please. This is where satellite remote sensing comes in. As you've probably heard by now, NASA has about 20 satellites orbiting the Earth, looking down, making various observations of the land surface, the atmosphere, and the oceans. There are many that are related to the water cycle, such as measurements from the aqua satellites shown here in the upper left. However, most of those observations using the conventional remote sensing techniques, which measure various wavelengths of the electromagnetic spectrum, cannot penetrate below the first few centimeters of the soil column. So if you're interested in things like groundwater and soil moisture, they're not very useful. However, the GRACE mission, which launched in 2002 and extended to 2017, and the GRACE follow-on mission, which launched in 2018 and is still active, are different. They actually observe changes in Earth's gravity field, which are related to changes in terrestrial water storage. And in that way, they are not limited in the depth of penetration. They can actually observe changes in water stored down to the base of the deepest aquifer. Next slide, please. The way they do this is it's actually two satellites orbiting the Earth in tandem, one following the other, about 200 kilometers apart. It turns out that variations in Earth's gravity field, which are related to variations in mass at the surface, perturb the orbits of satellites in a predictable way. Therefore, as the two satellites approach a large mass anomaly, like a mountain range shown here, at first the first satellite is pulled forward and the distance between the two satellites increases. As the satellites pass over, the first satellite sort of held back, and the second satellite is pulled forward by that mass anomaly, and the distance between the satellites becomes smaller. Now, GRACE and GRACE follow-on are amazing because what they're doing is they're constantly making measurements of the distance between the two satellites with extreme precision. I mentioned before the satellites are about 200 kilometers apart. Every 5 seconds, using microwave and now a laser ranging system, GRACE and GRACE follow-on make measurements of that distance down to a micron level, which is about the size of a red blood cell. Over the course of the month, collecting all these measurements, geodesists are able to put these data into a regression model on a supercomputer and come up with a new map of Earth's gravity field. Because the measurements are so precise, we can actually see changes in the gravity field from month to month that are related to changes in mass at the surface. So you can imagine mass changes, things like atmospheric circulation, ocean circulation and tides, and over the land, the largest source of mass variations are changes in terrestrial water storage. So all the water stored on and in the land surface. Next slide, please. So this animation shows you an example of what we get from GRACE. It shows time series of anomalies of terrestrial water storage. So that's the water stored on in the land relative to the long-term mean. The red areas are places where it's drier than normal at a given time, and blue areas are where it's wetter than normal at a given time. Now we can focus in on an area of interest and come up with a time series of terrestrial water storage. The time series shown here is in units of cubic kilometers of water. A cubic kilometer of water, to give you some idea, is about 1/30th of what Lake Mead, the largest reservoir in the US, can hold when it's at full capacity. So these are huge variations, this time series varying from about -200 to +200 cubic kilometers of water in this part of Africa near the Okavango Delta. Next slide, please. What is terrestrial water storage? Well, terrestrial water storage is basically the integration of all the water stored on and in the land surface. It's all the groundwater plus the soil moisture in various layers, plus any surface water and snow. When you look at a time series of terrestrial water storage over a location like Illinois, which is one of the few places in the world where in situ observations are available of all these components, this is what it looks like. So this is a time series based on in situ observations. The blue is groundwater. The red is superimposed on that is soil moisture. The white, you can see just barely on the top, is snow. And then surface water, it turns out, is so small you wouldn't even be able to see it on this time series. You can see that there is both a seasonal cycle and interannual variability to the groundwater and the soil moisture. The soil moisture is the dominant component here. It accounts for about 2/3 of the variability. The groundwater accounts for about 1/3 of the variability. And as I mentioned, in this case, snow and surface water storage are very small. But in other parts of the world, for example, an alpine region or a polar region, the snow might be the dominant component. And a place like the wet tropics, like in the Amazon, the surface water storage is actually the dominant component. Now, what GRACE gives us is just the top contour. The changes in total terrestrial water storage doesn't tell us anything about the individual components. Next slide, please. So this is an example in the Central Valley of California. It shows how terrestrial water storage changes based on GRACE observations. As you know, the Central Valley is a place where there's a lot of agricultural productivity. It's also been hit by several droughts, and farmers really rely on the groundwater for irrigation in this region. Because of the combination of the droughts and the reliance on groundwater, you can see that the time series has a general downward trend over the longer period. Next slide, please. Now, GRACE and GRACE follow-on are amazing because they're the only methods available for making global observations of total terrestrial water storage, including groundwater and deep soil moisture. However, there are many challenges to making use of these data. First of all, the spatial resolution is very coarse. It's on the order of larger than about 100,000 square kilometers. So remember the map I showed you of Illinois? Well, GRACE can really only tell us the total terrestrial water storage variations over the entirety of Illinois. The temporal resolution is also coarse. It's a monthly time series. Even worse than that, the data are typically not available for 2 to 4 months after real time, which means they're not very useful for real-time operational applications, although there are quick look products available within a couple of weeks of real time. Beyond that, terrestrial water storage is an unusual observation. It combines the groundwater, soil moisture, surface water, and snow into a single quantity, whereas of course we prefer to have those individual observations. And then it's also it's a relative measurement. We can't estimate the total groundwater in storage, for example. We can only tell about the changes in time relative to the long-term mean. Now, there is a solution to all of this, and that is data assimilation. This is where we combine data from the GRACE and GRACE follow-on observations with other higher resolution, more timely observations within a sophisticated numerical model of the water and energy cycle processes at the land surface. Next slide, please. When we do that, we get maps like what are shown here. The left shows the root zone soil moisture, and right shows shallow groundwater, and these are animated over time. And what we're showing is actually has been converted to a wetness percentile. What that means is that each location, if you're in the second percentile, which is the darkest red, that means it's only been drier than that 2% of the time going back to 1948 at that location and during the same time of year. If it's in the 98th percentile, that means that it's only been wetter than that 2% of the time going back to 1948 at that location and time of year. You'll notice that the map on the left, the root zone soil moisture, responds much more quickly to atmospheric variations than the shallow groundwater does. The shallow groundwater sort of integrates over time the longer term variability. Now, if you were paying attention, you may have noticed we just passed in 2012 that major drought that covered most of the US. And now the US is recovering. We're in 2015 now. And as you'll watch, you'll see that it starts to become fairly wet in the central and eastern US. You may recall an extremely wet couple of years that we had in these regions. Coming up now, we're in 2018, and it'll start to become wet first in the soil moisture, and now in the groundwater, and now it's extremely wet, record levels, in fact. And then over time, as we pass into 2020, 2021, things start to become more normal. In the western US especially, it just seems like drought after drought after drought. Next slide, please. Here's another example showing Europe, and Western Europe had a series of pretty serious droughts over the past several years. And this is a time series that begins in 2017. It's already dry this time, and this is highlighting that we have surface and root zone soil moisture and groundwater products. And you'll see that during this period, Western Europe is, much of Western Europe is dry, maybe has some recovery in some areas, and then it's going to become drier pretty soon here as we get into 2019 in the time series. And there it is, pretty much all red, not good for agricultural productivity, obviously. And Europe has somewhat recovered, but still not back completely to normal levels at this point. Okay. Next slide, please. So this is my final slide. I'm showing you the URL where you can get some of our products, nasagrace.unl.edu. Our colleagues at the University of Nebraska-Lincoln have been posting these products going back to 2011. The product on the left was the first one. This is our standard US drought product. It's available for shallow groundwater, root zone soil moisture, and surface soil moisture. Again, these are percentiles relative to the long-term climatology, where reds mean drier than normal at the particular location and time of year, blue means wetter than normal. And these are available weekly, within a week of real time. They're actually also one of the inputs to the US Drought Monitor. The US Drought Monitor authors use them as one of the products that they look at when drawing their maps. The product in the middle is one of our newer products. It was available first in 2020, and this is a global groundwater, root zone soil moisture, and surface soil moisture product. Very similar to the product on the left. It's also wetness percentiles. The only thing that's a little bit different is that it has different inputs. The spatial resolution is a 1/4 degree, or about 25 kilometers, whereas our US product is available at 1/8 degree, about 12 kilometers horizontally. The global product is really a first of its kind. If you search the internet, you will not find many, if any, global drought products. I know there's one that's based on the SPI precipitation indices, but this is the only product that provides a groundwater and deep soil moisture indicator as well. The product on the right is our newest. This is a forecast product. What we do is we use the GRACE and GRACE follow-on data assimilation to initialize a forecast going into the future, and we produce 30, 60, and 90-day forecasts of a wetness and drought conditions across the U.S. And these again are for groundwater, root zone soil moisture, and surface soil moisture. Thank you so much for listening. I wish I could have been there in person. If you have questions or if you're interested, I hope you'll visit our website, nasagrace.unl.edu, where you can find out more about these products, and also a link to my email if you have questions. I'd be happy to hear your feedback if you've been using these products or you have questions about using them. Thank you so much for listening, and I hope you have a great rest of your day. Thank you.